Okay. Gonna switch to the team. Excellent. Okay. Hello, my name is Victoria Bennett from the Crowdfunding Hub, and I'd like to welcome you to today's webinar with E2E Energy Solutions. E2E is a Calgary-based power company that utilizes Alberta's expertise and geological advantages to provide industrial-scale, stable and sustainable baseload power, unaffected by weather conditions. Their patented technology allows for quicker installation and a wider range of locations for geothermal energy, helping to achieve the global net zero emissions target by 2050 while delivering cost-effective heat and electricity. Today, we are joined by Domenico Daprocida, CEO, Pierre Lacoste Bouchet, COO, and Hammad Zafar, VP Subsurface, who will discuss the technology in more detail. Welcome.
Thank you.
Today's format was we'll ask the team questions about their EGRRS technology, then we'll open up to the floor for questions. For those of you not familiar with live webinar, if you have a look at the bottom left-hand side, you'll see there's a chat box. Just pop your questions in there. And for those of us joining on social media, just put in the chat there and I'll be monitoring both and making sure that our social media questions get answered today as well. But probably the best place to start. Nick, what is geothermal energy?
Thanks, Victoria. Geothermal energy, it exists everywhere. It's in the form of thermal energy, and it's everywhere beneath our feet. So there's different systems around the world and different ways to use the geothermal energy. So geothermal energy can be used as a shallow applications where they just provide a loop for direct heat, or they tap into existing reservoirs, subterranean reservoirs, which is where we focus our energies on. So, and there's two sides of it. There's the direct heat and the power generation. E2E is focused on the power generation. When we look at geothermal, we know that wherever we are on the planet, when we dig deeper, we get hotter. And in certain regions, it's better than others and are suitable for conventional geothermal development. But in the rest of the regions, which is the bulk of the planet, these ideal aquifers are not available. So what we do is we enhance the aquifer, the existing aquifer, to create a scalable process.
So is that, what the EGRRS technology is, or can you just explain what EGRRS is? Because I know that's unique to you.
Yeah, so EGRRS, we take the existing reservoir that would normally be produced conventionally, and we target reservoirs with a minimum of 80 degrees in the reservoir. We drill into the reservoir, drill through it, down to the depth, to our target depth, the target temperature, and we produce fluid from the reservoir down the injection. And then we have a production well that's drilled, intersects, and we flow the fluid through the formation, which will be discussed in greater detail later in the presentation. And then the fluid, once it passes through the fractures, it's upgraded and is produced at the surface. So the advantage of the EGRRS system is we could take an aquifer that would normally not be viable for geothermal power generation, and we are able to enhance that and make it viable and scalable.
Great. So, I mean, you've already touched on, but what are the economic benefits of EGRRS?
Yeah, well, again, the economic benefits are we can produce power at a very low price, comparable with conventional geothermal, $80 to $100 per megawatt, or 8 to 10 cents per kilowatt in Alberta. That's what our modeling is showing. The additional economic benefits are regions like Alberta. We have some suitable geothermal that can be produced conventionally, but is probably not a very viable project. But with EGRRS, we're able to create a scalable model and enhance the existing brines, and then produce them at the surface. So we're able to do large-scale geothermal power generation in areas that typically can't, and be competitive with conventional geothermal.
That's great. So, Hammad, we often hear about the challenges of the temperature gradients. How does E2E's technology address those challenges?
Yeah, great question. And Nick touched on that already. So allow me to explain what's the gradient. So essentially, we observe the temperature around us at surface conditions. And as we go deeper, make a journey towards the core, the center of the Earth, the conditions start to change towards the core conditions. The temperature starts to increase. The rate at which this temperature increases is what we call as gradient. Why is it different in different parts of the world? It's different because the core of the Earth, it protrudes wherever it finds less resistance. So wherever the core has made its way towards the surface, you will find higher temperature sooner, and we'll say that we have a higher temperature gradient in that area. When that higher temperature gradient meets a body of water, it creates a very favorable condition for geothermal. The body of water is heated. That heat can be extracted by extracting water, and we can put that heat to use towards electric energy, direct heating, whatever the case may be. However, those conditions where there is favorable geothermal gradient and there is a very favorable large water body, those are few and far between. As Nick already mentioned, there's very few places in the world where you'll find a aquifer at ideal conditions. So there's a need to combine the two, and that's where EGRRS fits in. It takes in water from any aquifer, doesn't have to be at the ideal temperature, and it takes in rock at high temperature, doesn't have to be any specific rock. There are certain conditions we have to respect, but it puts the two together, and we are able to upgrade the temperature of water from the aquifer and put that to use. So that in a nutshell is how EGRRS tackles the challenge of geothermal gradient.
So what I'm hearing then is you're actually opening up more locations for geothermal because of optimizing the temperatures and being able to use those gradients.
That's exactly right. Yeah.
So what is the impact on the surface water and aquifers by using EGRRS?
Yeah. So again, we are using subsurface aquifers and combining them with hot formations, which are deeper down. The process does not have any draw on surface waters. We don't use surface waters. They could be used in the process of construction, etc., but that's minimal use. Over the life of power generation process, all the draw is from a subsurface reservoir. Now, even for a subsurface reservoir, all the fluid we draw is returned back to that reservoir. So there's very little change to the overall mass balance in the subsurface aquifer. So really, we are using the fluid that nature offers us in abundance to harvest heat that nature offers us in abundance as well.
Perfect. So what is the permeability profile to get the best locations?
No, great question. So permeability is one of those things which lies at the heart of every oil and gas and geothermal conversation. In general, we all hear the higher the permeability, the better, and for good reason. The higher the permeability, the lesser the parasitic losses that you will get in the system, essentially. Now, what role does it play in EGRRS process? So we draw water from aquifer. Again, it provides a decoupling of dependence on a specific formation. If in a conventional geothermal, there is dependence that the hot water-bearing formation must be very highly permeable. In EGRRS, you just need a permeable formation. It doesn't have to be a very hot water-bearing formation. It just have to be a water-bearing formation. And you can use that permeability to your advantage and use that water, run it across the fracture network that we create in a rock that's best suited for temperature. We can create our own permeability through fracture simulation in such a rock. And then that water is routed through the channels that we create. And absorbs heat from that hot formation, brings that to surface. So that's how we tackle the permeability challenge.
Excellent. And it just sounds like, EGRS is much more versatile. Great. But Pierre, what is the difference between and the benefits between existing geothermal technologies and E2E's EGRRS?
Yes. In order to answer that question, I prepare 3 slides. So
Perfect.
everything that has been described by Hammad and Nick, so you'll be able to visualize. So it's going to be easier for you to understand.
Sounds good.
So first slide, I would like to describe, there is a few technologies in the market, or there is in fact one, which is the conventional, but 3 emerging technology at different technology readiness level. So I wanted to prepare this slide to compare conventional and the other system versus EGRRS. So let's start with conventional. Conventional is used for probably a very long time. So we know that the Roman was using the heat that it came to the surface and was using it for different purposes. So, but today there's the majority of the geothermal power or geothermal heat production, right, use conventional. So it's very, very simple as a technology. So you have an aquifer here, right? And you withdraw the brine from the aquifer and you bring it at the surface, where you can do basically 3 things. Use the heat for direct heat purposes, make power if the temperature is high enough, and or do both, right? And when you remove the energy, the temperature of the brine decrease, and you re-inject into the same aquifer. So it's very simple. It's a loop. So if you look at what we have, the emerging technology, there is the geothermal loop. Geothermal loop are very simple. It consists at drilling and sealing a well, where you recirculating almost indefinitely the water from I say water as a working fluid, right, to be transferred into to heat and or electricity if you have the capacity. So it's basically a borehole sealed and you just do a recirculation. So EGS now, EGS stands for Enhanced Geothermal System. It has been recently developed and demonstrated. It started what I call the engineered radiator, right, which is here. It started in Switzerland, and the result has been transferred to the University of Utah for the Forge project, where they created a engineered radiator. Following that, and not following that, I would say in parallel, a company in Nevada, Fervo, developed a commercial pilot based on this technology, and they in fact commercialize the power generated from an engineered radiator. And so in doing that, it allowed us to demonstrate the feasibility of our technology, because EGRS is very similar to EGS. And the only difference is where you do the re-injection here, right? So you can see that for an EGS, after you extract the energy from the radiator, you return back directly the energy to the radiator. While EGRS, we are re-injecting it in the aquifer. And as you can guess it, the working fluid is different. So the working fluid is made at the surface with water. Normally with water could be other chemical and also and injected into the radiator, while we use existing brine, right? And we are sending it down, which is the invention, to be enhanced. And this is what Nick and Hammad was mentioning. One enhanced through the fracture, it's bring to the surface. but not return directly into the radiator, but it passed through the aquifer. So now the aquifer become a preheater for the brine, and the water diffuse over time, right? And come at the aquifer temperature, let's say 100 degrees Celsius. Normally in AGS system, the injection is around 50 degrees Celsius. So the difference in temperature make the EGS engineered radiator smaller for a same amount of energy that you're going to bring at the surface. That means that if it's a smaller system, it become the capital invested for drilling and completion is less. So an EGRRS system is a combination of conventional, because we use an aquifer, and also a radiator, so a combination with EGS. And it becomes basically more efficient in GS system. So we are also more, because of less capital invested upfront, we becomes more economic, and also because the injection is a higher temperature, our radiator would last longer than an EGS system. This is an advantage over the system here. So just some keyword for your understanding. So thermal energy power needs to be larger than 100 degrees C. This is the rule of thumb in the industry. So everything lower than 120 degrees C, it becomes very hard to produce economically electricity. Having said that, the technology exists at lower temperature, but you don't make money. And if you want to deliver only heat at the surface, your customer needs to be fairly close. Energy resources. So we require high porosity in the aquifer here. Porosity is basically the hole that in the formation that will hold the brine, and high thermal induced conductivity of the radiator. The radiator needs to communicate efficiently the temperature from the formation to the brine. So we require a high flow rate, as was mentioning Hammad, and we need also descent chemistry, the corrosion and scaling. So that is basically a high level comparison between both technologies. Now the benefits. So benefits and also comparison, right? So technology readiness level. This is a scale used by NASA. 9 is it's deployed commercially several times, and 0 or 1 would be, for instance, just an idea on paper. And so a level 9, as I mentioned, it's demonstrated commercially. And so we put geothermal loop 7 because it hasn't been demonstrated commercially yet, but there is few locations where they are building geothermal loop in the world. And EGS has been demonstrated by Fervo, as I mentioned, so I put it at 8, but it hasn't been demonstrated at few locations. And we put a 6 because we are looking to pilot our technology. Aquifer selection. Yes, we are the only technology where we can choose the aquifer that we will use. And when we say selecting the aquifer, when we drill, normally you can have 3, 4, 5, 6 aquifer with different characteristics. And we have the ability with this technology to use the right one. EGS doesn't have aquifer selection because they don't use the aquifer, they're just passing through it. And conventional, you don't have aquifer selection, you just go with the hottest one. And you deal with the advantage or the disadvantage that this aquifer is going to provide. Geothermal loops, there's none of it because it doesn't use aquifer. Geothermal formation, so we use aquifer and radiator for EGRRS, so that make our energy reserve shared between 2 formation. EGS use only a radiator, conventional use only an aquifer, and geothermal loops only radiator 2. So additional potential revenue. So critical mineral extraction, it's possible with EGRRS. Would be very low for EGS. Conventional, it's possible, but less than conventional because you cannot select your aquifer on the basis of, for instance, lithium content, right? And critical mineral extraction for geothermal loop, it's none because, as I mentioned, the wells are sealed. So how are we different? So levelized cost of electricity. So for those who doesn't know what is levelized cost of electricity, it's all the cost per year, let's say 20, 25 years, right? That is discounted. And also the energy is discounted for, so it's basically energy, the cost divided by the energy, and both are discounted. So lower is the cost, better it is. So we believe that EGRRS has a lower cost because the reinjection in the radiator is higher, the temperature, versus EGS, which is lower. So you need less energy to, you need less energy for the same amount of energy you bring at the surface. That makes you can design your radiator smaller. So smaller means less cost. So we believe that the cost of EGS is slightly higher than EGRRS. Conventional would be roughly the same. Conventional are normally built close to volcanoes or faults where you have water that would penetrate from the surface, be heated by a formation and bring back to the surface artesian, or I mean for the purpose of commercial. So you need to pump it a large volume to the surface. So we believe that we are equivalent to conventional. This is what our financial evaluation showed. And geothermal loop, unfortunately, it's very expensive because in order to create the surface and the resistance time necessary to bring the equivalent amount of energy for the other one is you need a lot of drilling, and drilling is very, very expensive. Technology scalability, EGRRS and EGS are about equivalent. So you can imagine that you can drill in different direction to extract more energy. Conventional, well, you have to deal with your own aquifer. And geothermal loop, you have to deal with the radiator, right? For scalability, you can drill more, but because it's so expensive, I remove a scalability point. Geographic location. So EGS and geothermal loop, in theory, can go everywhere in the world. Conventional, as I mentioned, close to volcanoes and faults. However, we extend the conventional area into sedimentary basin, and it's way larger than conventional can provide, but not as much as EGS or EGRRS or geothermal loop. Resource lifespan is, according to us, pretty good. The reason being is that we are sharing the energy between two formations, which is not the case for conventional, which is lower. EGS, it's good. However, this system is going to code faster. And geothermal loop, well, you don't bring too much energy at the surface. You will need to drill. So I remove one for lifespan. And eventually your radiator is going to cool. Also, you have only one radiator. And primary application that we are looking to use, EGRRS, is for power generation is high and direct heating medium. We are mainly focused on power generation, just for to let you know. Power generation for EGS is high and medium would be equivalent, but as I mentioned, lifespan should be shorter and slightly more expensive. Power generation medium for conventional and direct heating high, and power generation low and direct heating high also for geothermal loop. So hopefully the comparison help you to understand our technology and geothermal industry as a whole.
That was great. Thank you very much, Pierre. Let me give you humans back. So thank you for sharing your screen. Just switching back. Perfect. Next question. Who shall I pick on? Who shall I pick on next to ask the question? Do you want to pick up on that? Probably into a bit more detail about where EGRRS can be implemented, Pierre.
Yes, absolutely. So as I mentioned in the previous slide, so we are targeting oil and gas sedimentary basins, okay, with a decent thermal gradient. But why? Because oil and gas exploration, this is where you find oil and gas, right? And so to find the gas, so they do the exploration and they drill to confirm that they have the reserve, but sometimes they hit water, a lot of water and hot water. For oil and gas industry, this is a waste. So they close the well and they move on to another area or to another well to find out if there is oil and gas. But for E2E, in the sedimentary basin, this is a resource, and this is potentially a source of power and heat for our customers. So why it's important? Because when the industry drill, they keep information. So they keep the information on the temperature of the borehole from the surface down. Sometimes it's only at the bottom hole that there is the temperature, but this information give us an idea of the gradient, thermal gradient. We know when they hit an aquifer with a lot of water that is brought at the surface. So we know sometimes the characteristic of it. So the volume bring at the surface, you can have the temperature, and sometimes they take sample, they send it to the lab. So regulators, and in Alberta, they are doing it well. They are requesting information to the industry, and industry provide. Sometimes the industry has even more information than that on the aquifer. So my point is, we decrease our exploration, geothermal exploration risk in going to sedimentary basin, because we know the characteristics, or we can have a very good idea of where are those aquifer that we are looking to upgrade the brine temperature. And yeah, so all the information is available. So, and those sedimentary basin are found in Alberta, as you know, but they are found also in BC. You can find also large sedimentary basin in California, Texas, and Colorado, to name few. And same system are in Mexico, and you can find it worldwide, Middle East, for instance. So there's a lot of places where we can implement EGRRS and be successful.
Okay, brilliant. Hammad, what are the challenges around seismics?
Yeah, so that topic comes up every now and then. The main concern there is the effect of a fracture stimulation on. Are there any seismic changes that happen through fracture stimulation? So the effect of fracture stimulation in geothermal is the same, very similar to what the industry is familiar in from an oil and gas side for fracture stimulation. A lot of fracture activity has happened as part of shale gas and shale oil boom, if you like, in the recent years, in the last 10 years in North America and Canada. So the process of creating fractures for geothermal is very similar to the process of creating fractures for the shale gas and shale oil. Now, one area for us which is important to watch is the interplay of the man-made fractures and the fractures that might be occurring naturally in the rock, especially the large naturally occurring fractures, also called faults. Some faults are active, permeable, which means that if you put fluid across them, they'll take your fluid. So obviously that's an area we will want to avoid. It will be detrimental to the efficiency of our radiator. So that's an area we like to watch very closely, and it's an upfront study that has to be done to understand that the performance of the radiator that we create is not going to be affected by natural regional faults or natural fractures that are prevalent in that area. But other than that, it's a very similar process, and if anything, it's more forgiving because by our geothermal radiators are deeper than most of the oil and gas fracked wells that we know of.
Great. Thank you, Hammad. I've got a couple more questions to the team, and then I'm going to open up to the floor. I see we already have some questions coming in, and we have quite a few people watching online as well on social media. So great to see the interest. Pierre, what is the return on investment for a typical EGRRS project?
Yes. As we mentioned, so we are focusing on power. So considering a EGRRS power system, and it depends on a few things. So of course, the geology. So all geology systems are unique. So considering also the electricity sale price, right? The carbon credit that we are generating with our geothermal system, and also 30% capital tax credit from the federals clean technology investment program, we can expect a return on the investment for our customer between 20 to 30%. And other jurisdictions also have their own programs. So you're talking USA, Germany, and Turkey as an example. And also in general in Europe, right? In France or Netherlands, they have their own advantages and incentive for doing projects. So 20 to 30% would be the range expected.
And I think I'm correct in saying, which surprised me, I always thought of this as being an Icelandic thing, but the USA actually has the most geothermal in the world now by quite a long way. So
yes, yeah. Other countries are coming fast. Turkey is developing the geothermal system, their geothermal industries very quickly. So yeah, we can expect that. I think USA is going to continue leading because technologically they are leading the development of technology. But it's going to be, I think, in different countries, it's going to be developed. So Japan, Philippines, and many countries, or even Pakistan, for instance.
So Nick, what are the opportunities that E2E's invention creates in Alberta? And I'm actually going to sort of, we heard yesterday Danielle Smith's announcement, the 50 million investment in the Alberta drilling specifically around geothermal. So if you can sort of, even speak to that, because that's brand new information that's really quite exciting.
Okay. Well, to start with, EGRRS, and geothermal in general, uses the same people and skills that the oil and gas industry use, which are in abundance here in Alberta and Western Canada. So it makes what we're doing really an ideal fit for Western Canada. And looking at Alberta, at the province, we have decent geothermal resource, but it's not conducive to power generation. It's power generation in Alberta is quite challenging and very hard to make viable. That's where we bring EGRRS in. So EGRRS, essentially, like Pierre did a great job discussing and showing you the slides, is a combination between conventional geothermal and EGS, enhanced geothermal, which are both proven technologies that are being implemented today. So it really de-risks EGRRS, because all we're doing is combining the two, putting the reservoir into an EGS system, which which acts as a preheater. So when we're re-injecting our fluid, instead of directing it directly into the formation, it's directed into the aquifer first, where it is upgraded to 80 to 120 degrees Celsius, depending on the depth of the aquifer and geothermal gradient. And from there, it's sent down to be upgraded to our target, 180 to 200 degrees Celsius, which is what we need for economic geothermal power generation.
Yeah. I just want to add that this announcement will decrease the overall cost if there's any breakthrough coming out of this investment, right? It will, as an industry worldwide, it would help the industry to decrease the cost and become competitive with other source of energy.
And I'm guessing also really put Alberta on the map for geothermal. So being a leading geothermal company in Alberta, that will also put eyes on you, which is never a bad thing.
Yeah.
I'm going to open up to the floor. Got some really great questions come through, so I'm just going to pile through those. And if you have any more, just pop them into the message. So Ryan is asking, is the EGS and EGRRS radiator area in the Cambrian granite area below the sedimentary areas?
Maud, do you want to take that one?
Yeah, I can take that. Yeah. So EGS demonstration that was done in the Precambrian. EGRRS, yes, you can do the same in Precambrian. Does it have to be Precambrian? The answer is in the geothermal gradient of the area. If you hit those temperatures at which you're looking to generate power in the Precambrian, then it will have to be Precambrian. But if you hit those temperatures within a sedimentary basin, a shallower horizon, then there is no reason to go into Precambrian.
Okay, great. Scott asks, do you have a pilot site location selected or proposed?
Yes, we do. We have two. We announced one last year, which is a project in conjunction with the town of Rainbow Lake, the municipality. And the purpose of that project is to provide heat, well, to basically get the town off fossil fuels. So we're going to be providing the heat and the power for the town. Well, where it's at right now with the Rainbow Lake, we're evaluating sites and talking with producers up there about acquiring a site. The other project, which we just announced a few weeks ago, is the Latitude 53 project. And we're doing that in conjunction with Novus Earth, Ormat Technologies, University of Calgary, and University of Alberta. And that project is coming up quickly. It's permitted. We expect to be on site working by January. Well, possibly not on site, but we'll be into the engineering and starting the project in January 2025, which is very exciting. The first phase of that project is actually a conventional well, which will be drilled, and it'll provide us the data that we're going to need to engineer the EGRRS system. So once we've captured all our data, the well is going to be converted to a producing conventional well, which will satisfy our customer. And who we're satisfying there is a commercial greenhouse developer. So it's 20 acres, and the crop that they'll be producing is strawberries. So it's an exciting project. And then following phase one, we're into phase two, which is focused on the power generation using EGRRS. So we're taking the same formation that we wouldn't be able to produce the power before. We're going to upgrade it using EGRRS to produce a 10 megawatt power plant to satisfy the power needs for the commercial greenhouse as well.
Fantastic. So strawberries from Hinton, from the heat in phase one, revenue generating early next year for E2E, and then phase two, the 10 megawatt EGRRS system doing power and heat. So yeah, hopefully, Scott, those very good pilot projects that actually will demonstrate and actually prove and generate revenue for E2E and answers your question. Patrick asks, what's the expected resource lifespan of an EGRRS system?
Well, we've we've run a number of simulations on EGRRS, and we've run them out 20 years. And we've also done a comparison with EGRRS and EGS, which is being used today. So by using EGRRS and implementing the reservoir, we're able to see up to 50% improvement in efficiencies, which is enormous and can make the difference between a viable project and a non-viable project. And Western Canada is the perfect example of that, because we're not the top location for geothermal, but we're not the bottom either. We're kind of in that middle ground where power generation is challenging, but with EGRRS, we open up all those areas that we can produce.
Perfect. Any other questions? We've had 3 really good questions there. I'm just having a check on social media. No. Nick, do you want to give a sort of closing statement?
Oh, sure. Yeah, so because we're here in Alberta, it really makes sense to look at technologies like EGRRS or other geothermal technologies. Where we do this here already, our oil and gas sector has been doing this for decades, producing heat. They've just been putting it back. They've been producing the oil and gas and re-injecting the heat energy. So what we're doing is we're targeting the heat energy. So it's a complement to the oil and gas industry. We're not competing against them or trying to replace them. We're working alongside them. We're producing renewable energy and they're producing oil and gas. We're going to need oil and gas for a period, but as the transition happens, we'll have the ability to scale up the geothermal on the same sites and slow down or decrease production on the oil and gas as the demand tells us.
Yeah. No, I think that's right. It's all about transition. I always say we didn't get off our horses into cars. And so this is actually using resources of people, in a positive way and still hitting our long-term goals. Oh, I do have another question. So I'm just going to sneak it in. Patrick asks, how quickly does the quality of heat degrade over that 20-year lifespan?
Okay, the heat degrades at startup. There's quite a sharp degradation, and it falls down about 20%, Pierre? Yeah, about 20% where it'll plateau. And that plateau is a gradual decline. We've run it out 20 years, and we've been able to demonstrate that we can produce the same power on day 1 as we can on year 20.
Right.
Yeah, and this, right. And this difference can be used in 2 different ways, right? Mm-hmm. So for a same amount of energy at the surface, the radiator for an EGRRS system will be smaller, right? So if it is smaller, then you have less capital investment. So if we take that at our advantage, then the energy at the surface, even though with the decline, you would stay in an environment where you are economic because of the capital investment is less. So this is one of the advantage over EGS.
Excellent. Thank you.
So if I may add another thought there.
Yeah.
The EGRRS process uses subsurface aquifer. So a subsurface aquifer, by virtue of the gradient, geothermal gradient, is already at an elevated temperature. So you could be at 60, 70, 80, whatever that number is. We don't know. It depends what nature gives us. So now you're drawing less heat from your target formation than you would if you were using, for example, an EGS system or just a closed loop circulation system where you're pumping water at surface conditions and your heat exchange is happening between surface condition temperature and reservoir rock temperature. Then there's a bigger conversation on how quickly the temperature of the formation is going to decline. What's the transmissibility of that rock? How well it is connected to a larger heat source? Those are very, very relevant, very valid questions. Now, EGRRS provides you a second level of heat source, if you like. So there is a preheating happening in a subsurface aquifer. You're already drawing water at at 80 degrees, 70 degrees, wherever is the hottest aquifer that's usable. And then the delta that your target formation is providing is actually smaller. So that in itself prolongs the life of that heat source. How long are the heat sources able to keep up the supply? At this point, we are at a very early stage of the industry. I don't think anyone in the industry can vouch for any heat source at this point. I think we're all learning.
Perfect. So E2E is currently in the coming soon phase of their capital raise. If you go online to the website, you'll get more information. You can sign up. We'll actually send you an email with the link as well to get more information about the campaign and get first access to it. And there are upcoming webinars. We already have, if you go onto Eventbrite, next week's webinar with Sabina, who is the Chief Sustainability Officer, and Nick, looking at the sustainability and ESG, both the vision and also the implementation, the work that they've done to date. I just want to say, a thank you to Nick and Pierre and Hammad and to everybody attending today. There's the button on the screen. If you click the Learn More button, you'll be able to sign up. But thank you to everyone attending today and for asking those really interesting questions. Hopefully you got what you wanted out of today. And the other thing just to say is, I'll bring the humans back, just to say, just follow us on social media and watch out when the campaign goes live. You'll be able to invest, or alternatively, if you sign up, we'll give you first access. Thank you very much, everybody, and enjoy the rest of your day.
Thank you very much, everybody.